the free response question number 3 on the 2016 E&M AP Physics C exam. And here we go. So we've got a situation, a conducting bar of mass M and length L, and negligible resistance, that's interesting, is connected to a long vertical conducting rail of negligible resistance. Okay. I see, compared to this resistor R. The two rails are connected by a resistor R at the top. The entire apparatus is located in a magnetic field of magnitude B directed into the page, as shown in the figure. The bar is released from rest and slides without friction down the rails. What is the direction of the current in the resistor? So, as this thing slides down, what's happening? We are getting more and more area in here, more and more flux going into the page. That's going to induce a current. By Lenz's law, it's going to induce a current that will oppose the rate of change. So by using the right-hand rule, if you're getting more and more and more flux into the page contained by the loop will create a current that will circulate this way to make my thumb go up, to oppose the rate of change. So if it's circulating like this, that means that the current will go to the left. There's another way of looking at it. Put a little, let me redraw this. So here's my bar that's sliding down with this velocity, and here's the flux. Now, if this is sliding down, put a positive charge in there and use, F equals QV cross B. So the velocity is down, and if I use the right-hand rule, I'm going to rotate my paper because I can't rotate my wrist, but the velocity is down like this, and then I cross my fingers towards the magnetic field. My thumb is like this. That means that positive charge carrier is going to get pushed to the right. But if this is getting pushed to the right, then all these charges are getting pushed up, and this is getting pushed to the left, and this is getting, so it's the same kind of deal. Okay? So that's why it's to the left. So hopefully you got that. Now, this one's a little more subtle. It says, for part B, is the magnitude of the net magnetic field above the bar at point C? So here we are at point C. Is the magnitude of the net magnetic field, not flux, but field, magnetic field, C, greater than, less than, or equal to the magnitude of the net magnetic field before the bar is released? Well, look, take a look at this. Here's part C right here. There's a magnetic field strength that's going into the paper here. It's going down. But because this thing is now moving down, this is creating a current that's circulating like this, and that's going to induce a magnetic field that's going to be in this direction. It's going to be up. Now, this is not up. The induced magnetic field is not up because this magnetic field is down. It's up because I'm getting more and more flux contained by the loop that's down. The rate of change is down. But anyway, but the induced magnetic field is up. So because the induced magnetic field is up and the starting field is down, they will serve to cancel each other out, and so the field will be less than. And because the induced field, I'd like to justify my answer, the induced field opposes, is it oppose or appose? Oppose. Opposes the constant field or the original field. It's in the opposite direction. And you might want to put due to Lenz's law, something like that. Okay, now while the bar is above point D, so we're above point D, is the magnitude of the net magnetic field at point B, D, greater than, less than, or equal to the magnitude of the net magnetic field before the bar is released? And it's going to be equal to, because this circulating current right here is going to induce a magnetic field, but it's going to be contained by this. Now it will go out into the world, but we assume that outside that loop it's essentially negligible.
I guess technically it's greater.
I don't really, it's going to be interesting when they publish the official solutions, because I suppose it could be greater, but it's really, really, really weak. So I'm going to say that,
Hold off on that one.
yeah, you might want to hold off on that one. I would say, though, that the induced magnetic field in here, or outside the loop, is negligible. And thus the magnetic field at point D remains the same.
So you're going to resist that change?
Yeah. Can I help you real quick?
Paper towels.
What Mrs. Harrington wants, she's going to get. Here you go.
Thank you.
Paper towels. All right. Now, ooh, gross. Okay, now let's do the next part, see if we can get this done. Express your answers to part C and D in terms of M, that's the mass of this thing, L, R, that's the resistor, and B, and physical constants as appropriate. Write but do not solve. Hey, write but do not solve a differential equation that could be used to determine the velocity of the falling bar as a function of time. Okay, well, now we got to use a little bit of our mechanics. Let me redraw this thing like I did before. Here's the falling bar. It's got a velocity v. It's got flux inside here. We've got a resistance R, and so on. But I'm going to draw a free body diagram of this guy. Okay, now we're going to have two forces acting on this. We've got mg, and then we've got this magnetic force, F sub b. Now F sub b, now mg is a constant, it's down, but what is this? This is going to be Phil Crosby, I, L times b, and here's the field that it's falling through. So if I sum the forces in the y direction equals ma in the y direction, so we want it in terms of the velocity. We want velocity. Okay, so here's what we're going to do. And let's make down positive y. Well, I got mg, then I got minus I LB. Okay, yeah. And that's going to be equal to MA. Now this is cool because A is dB dt. That's the rate at which I'm changing the downward velocity. And this is a constant they're given. This is but look, I doesn't work with what they want. They want it in terms of these variables right here. So we have to get I in terms of what we're given. Well, we know that the induced voltage. This is motional EMF. So this is going to be BLV. But now this is v as a function of time. This is, and this is v as a function of time. So now, but E also equals IR. So I is going to be equal to E over R, which is BLV over R. So now I'm going to substitute that in here. And so I get mg minus BLV over R times L times B equals m times dv dt. And there we go. I'm done. I probably should clean this up a little bit. It says derive but do not solve. mg minus b squared L squared V over R equals m dv dt. This is a differential equation in terms of V. And yes, we can use that to solve for velocity.
What exactly does it mean by solve? Like, is it solve when you have V equals?
Well, I'm just doing part C right now.
So it says write but do not solve. Like, where's the line there where you've written it but not solved it?
Yeah, I wrote it. I didn't solve it. Solving it means what is the velocity? What is the equation for velocity that when I take its first derivative and plug it in here, this works? That's what solving it means.
So, like, if you solve it, do they deduct points?
No, they probably stop right there. I think we have to solve it in part. Yeah, I mean, I think we're going to have to do it anyway. But this is all we need for part C. So you have to be, kind of clever in recognizing this and then setting all that up. That's pretty hard. So let's see if we can do part D now. Part D says, determine an expression for the terminal velocity. Oh, terminal velocity. What does terminal velocity mean? Yeah, the net force is 0. So if I go like this, so F sub B equals mg. And what did we say this was? Here's the force right here. Oh, yeah. Oh, I'm sorry. We just take this equation. mg minus b squared L squared V over R. But now, what's the acceleration? If you reach terminal velocity, what's true about acceleration? 0. And now I can just solve this for V. V equals, we'll put this over here, and so we have mg times R over b squared L squared. Did I do that right? Okay. And that's my terminal velocity. So that's not so bad. And now we get to the lovely part E. And part E says, derive an expression, in terms of the terminal velocity and all this, and physical constants is appropriate. Derive the expression for the power dissipated in the resistor when the bar is falling at terminal velocity. Oh, okay. So the power equals I squared R. So I think we have an expression for I. And it's just going to be BLV over R. But the V is the terminal velocity over R. Well, we have to square all that times R. So I suppose that power equals B squared L squared B sub T squared over R. And that's what I'm getting. And again, I have no way of checking this, because, except for you guys right now.
When I did the test, I thought I was asking for things in terms of like not terminal velocity. So I took the terminal velocity equation from D, plugged that in there.
Oh yeah, and you know what? If you here's the terminal velocity, right? In terms of all this junk. So I suppose you could take all of this and plug it in here if you want to. But why? Now, here's why they didn't want you to do that. What if you made a mistake up here? They don't want a mistake in part D to prevent you from doing part E. I mean, you could get part D wrong and still get part E correct. Hello, I'm answering your question. So that's why I think we got one more part F. Using your differential equation from part C, derive an expression for the speed of the falling bar as a function of time. So you have to solve this differential equation. Let's give it a shot. Let's see here now. We have to separate variables and all that sort of thing. mg minus b squared L squared. Well, let's multiply everything by r. So r mg minus b squared L squared v over r equals r, well, not over r, I multiplied by r, times rm dv dt. So now what I'm going to do is do this. I'm going to put 1 over rm times dt equals dv over rmg minus b squared L squared v. And I think I've separated, did I do that correctly? I divide by rm. Yeah, I think this is good. Huh. And then what I'm going to do is, I don't know, do a U, like let so what is du? Du equals negative b squared L squared dv. So dv equals du over negative b squared L squared. So I'm going to substitute that in for dv. I'm going to substitute this in for the denominator, so I get 1 over rm times dt is equal to oh, okay, that makes sense. Shh, can you guys stop talking while I'm doing this? Because I'm trying to get this done in 5 minutes. And it is distracting. So this is going to go up here. So I have a du over u, but I've got this negative b squared L squared. So I'm going to multiply both sides by negative b squared L squared, and I get negative b squared L squared over rm times dt equals du over u. Okay, and then we'll make this from now we integrate. From 0 to t, and then from u naught to u. And so here we get negative b squared L squared over r times m. Now, one thing, if you're following along, please try to help me if I drop a variable or a negative sign. I want some help here. Equals, this is the natural log of u over u naught. Now I need to back substitute. So u equals rmg minus b squared L squared v. What is u naught equal to? Well, u naught happens when t is equal to 0. When t is equal to 0, the velocity is equal to 0. It's starting from rest. So that means this term is 0, and it's just going to be rmg. So we have negative b squared L squared. Okay, so you see why you're probably never going to have time to get to this. The natural log of rmg minus b squared L squared v over rmg. Now what are we going to, times, you didn't catch that, times t, right? Well, you can do it. Now we're going to we're going to raise it to the power of e. E to the negative b squared L squared over rm times t. Now, by the way, I bet you, if I did this right, all of this, well, rm over b squared L squared better come out to be units of time, because rm over b squared L squared is tau, right, when we talk about exponential functions. And this is going to be equal to 1 minus it's going to be equal, no. Don't get ahead of yourselves, Blake. It's going to be equal to rmg. No, doggone it. Hold on. Sorry. This happens when I try to rush. You just get rid of the natural log. It's just equal to rmg minus b squared L squared v over rmg. So multiply, put that on the other side. So rmg times e to the negative b squared L squared over rm times t equals rmg minus b squared L squared v. Okay, now the bell is about to ring, so here's what I'm going to do. Just take this and solve it for v, and you're going to get that exponential function, I think. Unless I dropped a variable here or something like that. Anyway, we are out of time. So you guys can get ready to go. I'm going to finish this right now. Let's see. I got to see if I'm going to. Yeah, I think that's going to. So it's rmg times 1 minus e to the negative b squared L squared over rm times t all over b squared L squared, right? And there's my answer. What? That was easy. No problem.
That was a hard problem.
That is all.